So Unit 3 deals with polynomial functions. Let me give you an example of what I'm talking about when we discuss polynomial functions. We're going to be dealing with functions that are more than 2-second degree. In other words, third degree and above are the polynomial functions we're going to be dealing with in this unit. Here's a cubic function, which is third degree, 2x cubed plus 5x squared minus 3x plus 1. All right. Again, we're also going to look at functions of higher degree, let's say nth degree. In other words, it might be fourth degree, it might be fifth degree, and so on. All right. Now, the main topic of the foundational aspects of this unit are roots and zeros of polynomial equations and functions. Equations have roots or solutions. Functions have zeros. And you can see in this example, and I'll let you copy this down before we talk about the example, but we're going to look at an example of an equation and of the function. Okay, so roots and zeros are basically the same thing, but we use them in different contexts. We use the word root or solutions as whatever satisfies an equation, the answers to an equation, if you will. Whereas we use the word zeros to represent what satisfies a function. Now, what satisfies a function is wherever the function crosses the x-axis. Those are called x-intercepts. In other words, what is the x value where the function is equal to 0? Well, that would be a 0 of a function. So x-intercepts are actually zeros. Now, I've got two examples here. One of them deals with the equation format, and the other one deals with function format. X squared plus 4x plus 3 equals 0 is a quadratic equation. We can factor it into x plus 3, x plus 1 equals 0, and then see that our roots are -3 and -1. Those are the values that satisfy the equation. Well, over here, I've got the same expression, x squared plus 4x plus 3, but it's not equal to 0. It's equal to f of x, function notation. Well, I'm going to factor it exactly the same way. I'm going to get exactly the same answers, but I'm not going to call them roots this time. I'm going to call them zeros, because these are the values that satisfy the function. These are the values that zero out the function. In other words, if I were to graph this quadratic equation, I would have a x-intercept at -3 and at -1. Those are the x values where the y value is equal to 0. Therefore, they zero out the function. F of x is just the same thing as y. It's our output. X is the input. F of x is the output. All right? Now, we're learning all about just the basics of functions. And then we're going to put it all together and do some problems. All right. In order for us to know what we need to know, do what we need to do, we need to understand the fundamental theorem of algebra. This is on page 503 of your book. So I'll let you copy this down. Okay, so what I've done here is I have given you the shorthand version of what these theorems are. Okay, I've given you the everyday layman's terms. So the fundamental theorem of algebra basically says that every equation has at least one root in the complex numbers. Now, what are the complex numbers? Things like 2 plus 3i, right? So something like 2 plus 3i, you don't have to write this. 2 plus 3i is a complex number. Well, is this a complex number? 4 plus 0i? Yes. That's a complex number, right? 4 plus 0i would be a complex number. Why wouldn't it be? Isn't it in complex number form? Is 0 a number? 0 is a number, right? It's an integer. All right? But what does it simplify to? Just 4. So 4 is in the set of complex numbers. Okay? Therefore, any of our solutions would be considered in the set of complex numbers. So therefore, there is a corollary. A corollary is just an additional statement. A corollary to the fundamental theorem of algebra says that the degree of the polynomial is the same as the number of roots. So if our degree is third degree, how many roots are there? 3 roots. If our degree is 15, how many roots are there? 15. Now, some of those are going to be real, some of them are going to be imaginary, but they're all part of the complex number system. If it's real, it's in the complex number system. If it's imaginary, it's in the complex number system. All right? So, it's just the way that that works. So far, these things that we've learned are things that are very important for us to know about. All right, now, here we are going to see, I'll tell you what, let's pause, let's not write this one down yet. Let's go to this. Okay, so copy down the remainder theorem. Okay, so the remainder theorem is a theorem that says if we have a function f of x, let's say, then f of a is the remainder of the problem or the expression f of x, which is whatever the polynomial is, divided by x minus a. Okay? So if we were to do long division, for example, something like x squared plus 2x plus 3 divided by x minus 2, we could save ourselves a whole lot of time by using the remainder theorem. The remainder theorem says that the remainder is just the opposite of whatever's in this expression that we're dividing by. Plug that number into the function to get f of a, and you have just found the remainder. Now, we're not ending up with that the expression that we call the depressed polynomial. We're not ending up with that we would get if we did the long division, but we can immediately find the remainder by just plugging in the opposite of whatever this value is that we're dividing by, this expression. So in other words, the opposite of negative 2 is 2. Well, that's our a value. Okay? So if I take my a value to immediately find the remainder, plug 2 into the function. So f of 2 equals 2 squared plus 2 times 2 plus 3 gives you 11. That's your remainder. So we immediately find the remainder. This is also called synthetic substitution. Okay? It's like synthetic division in that it gives you your remainder, but it doesn't give us the polynomial that's also part of the quotient. Okay? All right? The remainder theorem leads us to allow us to do this example. All right, so take a look at example 2. Here, I called it example 2 because I had previously shown you a little example. It doesn't really matter what number you call it. It says find all the roots of x cubed plus 3x squared minus 10x minus 24 equals 0. So I'm going to let you copy down the process here, and then I'm going to explain it. So here we have a cubic polynomial. All right, it's greater than quadratic. We haven't had to find roots of anything greater than a quadratic polynomial to this point. So this is something different. Now, what we're going to do here to start with, and this is kind of just wetting our whistle, this is just getting ourselves started with finding roots and factors of higher degree polynomials. What we're going to do is we're going to try some solutions. We're going to try solutions maybe between negative 4 and 4. All right? And it just so happens, if I try the possible root negative 4, it works. All right? If I try this root negative 4 and I do my synthetic division, I come out with 0 for the remainder, which tells me that negative 4 was actually a solution. So I'm just guessing. I'm just getting, all right, I'm saying, all right, well, I have no idea what the solution is, what the roots are. So I'm just going to choose some small integers and see if they might possibly work. Well, guess what? I guessed really good. Negative 4, and I got it from the book, okay? Negative 4 works out. So we see that negative 4 is a solution because the remainder, when I do synthetic division, the remainder is 0. Now, after the synthetic division, I end up with what's called a depressed polynomial, which comes out to be x squared minus 1x minus 6. Y'all know how to do this, right? All right. Now, I don't know exactly why they call it a depressed polynomial, But think of it like this. If I press down on something, it's compressing it, right? All right? If I want to depressurize, I'm going to let off the pressure. All right? Well, what am I letting off? What am I taking out? I'm taking out one of the factors, one of the roots. And what's left is this polynomial expression. So that's maybe why they call it a depressed polynomial. All right? So here we go. We can now factor this depressed polynomial into x minus 3 times x plus 2. And what does that leave us for our roots? Positive 3 and negative 2. Along with the original root that we guessed right on, and that was negative 4. So what are the three roots? I got a degree of 3. It needs 3 roots. What are they? 3, negative 2, and negative 4. All right.
You're just guessing when it comes to...
Yeah, this first one we just guessed. Now, we're not going to have to do a lot of the guessing. The whole reason I did the guessing part here was to use a few strategies, all right, in finding the roots of a polynomial that's greater than second degree. All right. Now, what were some of the strategies that we used? Well, we used synthetic division, right? All right. Synthetic division is very similar to synthetic substitution, except that synthetic substitution just simply gives you the remainder of whatever the remainder is. And if the remainder comes out to be 0, then that tells us that the number we plugged in was a root. All right? So we also used some of the strategies that we already knew. We factored the polynomial. We found out the roots of those factors. All right? So what were the factors of this polynomial expression? X minus 3 is a factor. X plus 2 is a factor. And what will be the third factor? Excellent. Who said that? Very good. X plus 4, because the root is always the opposite sign as what's in the factor form, right? So if my root is negative 4, then the factor is x plus 4. All right. Now, I want you to write down the factor theorem. So this goes right along with what we just discussed with the roots are the opposite value of what's in the factored form. So copy this down. The factor theorem and the remainder theorem go hand in hand. All right? So the factor theorem says that the binomial x minus a is a factor of the polynomial f of x if and only if, when I plug a into the function, I get 0. That tells me that a is a root, right? So let's say that x minus 2 is a factor of this polynomial. Therefore, f of 2, when I take the opposite of negative 2, which is 2, and plug it into the function, I should get 0 if x minus 2 is a factor. And it is. Okay? So that's all the factor theorem says. It goes right along with the remainder theorem where I can plug that value in and get the remainder. Now, is the remainder always going to be 0 if it's not a factor? No. But if I'm dealing with a factor and I take that a value and I plug it in, what will the remainder always be? 0. All right. Now, let's take a look. This theorem says, complex conjugate theorem says if a complex number such as a plus bi is a root or a 0, then its conjugate a minus bi is also a root or a 0. So with that said, if I told you that 4 plus 3i was a root of a polynomial equation, then what else is a root?
4 minus 3i.
That's it. All right, so if this was a cubic, if these were roots of a cubic polynomial, all right, I would know that I've only got one more thing to find, one more root or 0 to find. Okay, so we're going to do some examples. We're going to start. Well, we'll erase that. We're going to start by doing this example. All right, now this is one that does not have an imaginary root. It's got a real root. All right, let's start over with this thing. Okay, so this actually comes from page 507 in your book, number 11. And what we're doing here is we are giving one of the roots of this polynomial expression, polynomial function. And how many roots will this function have? How many? It'll have 3 roots. So, they give us one of the roots. The one they give us is 4. So what we're going to do, like we saw earlier, we're going to take that 4 and we are going to do synthetic division to get our depressed polynomial.
Yeah, it'd be negative.
No, the root is 4. The root is 4. The factor will be x minus 4.
Oh, okay.
But the root is 4. So the root is what we use with synthetic division because we take the opposite of what is in the factor, right? Okay, so we're going to have our coefficients are 1, -6, 10, and -8. Okay, so then we go through the whole process of synthetic division, which is super easy. Bring down your 1. 4 times 1 is 4. -6 plus 4 is -2. -2 times 4 is -8. 10 minus 8 is 2. 2 times 4 is 8. -8 plus 8 is 0. We should get 0 because we know that 4 is a root. We knew we were going to get 0. We didn't care about that. What we care about is this depressed polynomial. So now let's write that down. It's going to be x squared minus 2x plus 2 equals 0. Now, the equals 0, it has nothing to do with the remainder. The equals 0 is because now I'm dealing with this equation and I want to simplify, or I'm going to try to solve it like I would other quadratic equations, either using factoring, quadratic formula, or completing the square. Now, for this one, it will not factor. There are not 2 factors of 2 that add up to -2. Therefore, we need to use a quadratic formula. You could complete the square, but that's going to be a pain. Go ahead and use quadratic formula. Remember, the quadratic formula is the opposite of b plus minus square root of b squared minus 4ac all over 2a. Now, let's do that. So, opposite of b, so you're going to have x equals -2 plus minus the square root, -2 squared minus 4 times 1 times 2 all over 2 times 1. So we all know how to do that. Now, like we've done before, we need to simplify underneath the square root. -2 squared is 4. Minus 8 is -4. So here's how it simplifies. I got positive 2 plus minus the root of -4 all over 2. Now, is that in simplest form? No. So we can simplify the root of -4. What does that become?
2i.
2i. So I'm going to just get rid of that and put a 2i there. Can I simplify it further? Yes, because all of these 2's are divisible by 2. So it's going to end up as 1 plus minus I. Now, how many solutions are right there? How many roots?
2.
There are 2. The 2 roots are 1 plus I and 1 minus I. So these are the 4 roots, 4 zeros, I should say, the 4 zeros of that polynomial function, cubic function. And notice that the conjugates, you will always have conjugates. If you've got one imaginary number, you're always going to have its conjugate as part of the solution. Okay? So that was pretty easy. They gave us a root. When they give us one of the roots, it's super easy, right? Okay? Now they're going to give us an imaginary root. It's a little different when they give you an imaginary root. Okay? Let's do it. Let me... Okay, so here you go. This is number 13 on page 507. The function is x cubed plus 7x squared plus 25x plus 175. The root that they give us is a complex or imaginary root, 5i. Can y'all see that? No, it's a 5i, sorry. This is 5i. Okay? All right. Now, if 5i is a root, what else is a root?
Negative 5i.
Negative 5i. Very good. So we know 2 of the roots automatically. Since we know 2 of the roots, we're going to be able to work backwards to find the remaining root. Here's how we're going to do it. Now, if I know what my factors are, if I know what my roots are, my zeros, then I can just write the factors, right? We can go back and forth. So I can write these in the form of the factored form. I know that there are going to be 3 factors in this problem, right? Because it's cubic. Cubic, degree 3, 3 factors, 3 zeros. All right, so the first one is going to be x minus 5i. The next one's going to be x plus 5i. Okay? So I'm missing one here. X plus or minus something. I don't know what it is. But we're going to use some of the strategies that we've learned before to figure out what it is. First of all, let's go ahead and put these together. Let's multiply these by the FOIL method. When I do the FOIL method, it's going to work out very nicely. These are like a difference of squares, right? So I can just do x squared minus 25i squared. I don't need to do the whole FOIL method because I know the middle parts are going to cancel out. Okay, so what does this simplify to? Very good. So I've got x squared plus 25. That's part of my polynomial. And then I've got this other part that I'm multiplying by that gives me this stuff. How am I going to find the rest of that stuff? I'm going to use long division. I know it's a pain, but it's easy. All right, so I'm going to take this polynomial, divide it by this, and that'll give me my remaining factor. So let's do it. X cubed plus 7x squared plus 25x plus 175. All of that gets divided by x squared plus 25. Okay? And we'll just pause there for a second. Okay, so finish copying that. Okay, so first things first. When we do this, we're doing x cubed divided by x squared to start with. But that's going to result in an x. We want to put that x over the x. Okay? So if I end up with an x, I'm going to put it over the x. So it's just x. Now I multiply back through. So x times x cubed squared is what? X cubed. X times, there's no x right here. There's no x squared. There's no x to give me an x squared. So what would I put in that blank? What would I put under this? A 0. All right? And then x times 25 is? 25x. All right? So what do? We change all the signs, right? Because we're really subtracting. We're going to change our signs. Okay, so what happens to the x cubes? Cancel. 7x squared minus 0 is just 7x squared. 25x minus 25x, 0. Bring down your 175. So plus 175. All right, it's going to work out so nice. Now I take 7x squared and divide it by x squared. What's left? 7x squared divided by x squared. 7. 7 times x squared is 7x squared. 7 times 25 is 175. And subtract. And I'm done. All right, so what is my remaining factor?
Plus 7.
X plus 7. Which means my 0 is?
7. Negative 7.
Negative 7. Very good. So we found that remaining factor, and that allowed us to find the missing 0. So we kind of had to work backwards. When they give us the imaginary root instead of a real root, we have to work backwards and use long division. But if they give us the real root, then all we have to do is use synthetic division with the depressed polynomial. Okay, but still, these are strategies that we know how to do. Now, what I'm going to do now is show you a video. And this video is going to encompass most everything that we did today and a little bit more. All right? But this video applies to what we do down the road. Okay? So it's like a preview of what we're going to be doing. Now, it's about a 10-minute video, and I might stop it in certain places. This is going to take up most of the rest of the class. But you're only going to have a few problems tonight for homework anyway. Like 3 problems. Okay? So homework should be easy tonight. But I really want you to pay attention to this video because I want you to compare what we've talked about and what he talks about. All right, so let's pause it.